Well, hello, physics. I actually tried recording this earlier, but it was too large of a file, so I have to start over from scratch. But that's all right. Um, I'm gonna do this in two sections. The first section, I'm gonna give you some definitions and equation. We're gonna go over some graphs and how to analyze them. In the second section, we're just gonna do some story problems. So for the first section, first vector or term that I'm going to talk about is a scalar. A scalar is just a value or a magnitude or a quantity. An easy example of a scalar would be mass. You can't do anything besides say, hey, this is how much mass something has. It's 2 kilograms or something like that. A vector, on the other hand, is a magnitude and a direction. If you've listened to Despicable Me, you know that already. But he's one of the villains in Despicable Me. So vector is a magnitude with a direction. An example of a difference between the two of them, if I said, for example, I'm going to drive 60 miles per hour. That's a scalar. I told you the value of it, 60 miles per hour, but I didn't tell you which direction. Now, if I said I'm going to drive 60 miles per hour east, that would be a vector because I gave you a magnitude, 60 miles per hour, and a direction, east. A distance is going to be a scalar. A distance is how far something moves. If you remember from your grade school days, you talked about distances being absolute values or absolute values being distances. That's why we get rid of the sign. Whereas displacement is how far you end compared to where you began. Um, so that can actually have a direction. For example, I could say I moved away from, you know, the dog 5 meters, or I walked toward the dog 3 meters. So it can have a direction, whereas the distance would just be I went 5 meters, I went 3 meters. So displacement does have a direction. A lot of what you're going to be doing in physics is getting used to using vectors for a lot of things, and we'll talk about how to add them and lots of things like that. We're not going to do that this summer, but we'll get to it early in the school year. This is the average velocity equation. It's v bar equals delta x over delta t. Something that I will note here, some of you are not used to this notation. If ever you see the Greek symbol delta, it just looks like a triangle. This means change. Okay, this means how much does something change by. So you'll see that a lot in physics. I better get a pen here handy. So let me define all of these different terms or these different variables for you. Delta just means change. It's not actually a variable by itself. Delta x is the variable, and that means change in position. Change in position you can think of as x final minus x initial if you want an equation. But that means change in position, and change in position would be displacement. Because x final could be bigger or smaller than x initial, this could be positive or negative. And because it can be positive or negative, it's a vector. Oops, I guess I was going to write that down there. I don't need that line then. So delta x is a vector. The next variable that we have there, on the right side anyway, is delta t. You can think of this as t final minus t initial. Most people do not. They just think of it as its own thing. But it just means change in time. Delta means change. T means time. And v bar means average. Average. If you ever see a bar on something, mathematically that means average velocity in this case. V is for velocity. The bar is for average. And using a little common sense, to find an average, we just add up and divide by 2. So we take our final velocity plus our initial velocity divided by 2. Let me back up a little bit. If you ever see me subscript a letter with an F, that means it's the final value of that. And if you ever see me subscript something with an I, it means the initial value. Some people will use a 0 instead of an I for the initial value. So you'll see a lot of books doing that, meaning the value at time 0. I like I because it doesn't necessarily have to be 0 then, whereas the x naught, as some people call it, would be at time 0. All right, I have created a graph. This is a position versus time graph. I know it's a position versus time graph because I see x on the y-axis, which is, I know that sounds weird, which is a position. This is measured in meters. And I see time on the x-axis, which is measured in seconds. And I want to figure out what is the average velocity over each time interval. So let me switch colors here. And let's do the first time interval first. So if I'm looking at this time interval from 0 to 10 seconds, let me list, so 0 to 10 seconds. Let me list what I know. I know my final position is, if I look here, the final position is 2. That's on the y-axis, meters. My initial position, if I look here, is 1.0 meters. So V bar would be the final 2.0 meters minus the initial 1.0 meters divided by delta t. Delta t would be 10 seconds minus 0 seconds, which is 1 meter, 1.0 meters divided by, oh, those were 0.0 there, divided by 10.0 seconds, which would be 0.10 meters per second. I'm putting the 0 there to represent that there's 2 significant digits. If you feel rusty on significant digits, don't worry about it too much with this lesson. We'll worry about it when school starts, and I'll be happy to help you with those. So that's just using the formula that I gave you, right? V bar is delta x divided by delta t. Just using that formula that I gave you right at the beginning. So let's do the second time interval. Let's do 10 seconds to 15 seconds. Same idea. So I'm going to say, okay, well, my delta x is going to be my final position. Final position would be 2. Okay, 2.0 meters. And the initial position would be 2. Oh, I didn't want an equals there. I wanted a minus. Minus 2. Oh, well, 2 minus 2 is 0. Well, that's interesting. So 0 meters. And then if I look at delta t, well, that would be 15 minus 10, which would be 5 seconds. And then if I did v bar, I would have delta x, which is 0, divided by delta t, which is 5 seconds. And obviously that would be 0 meters per second. We can see the units from the numerator as meters and the denominator as seconds. That should make intuitive sense, by the way. You can think of all of these as slopes. You can think of velocity as just your slope, because you have a rise, which is your change in position, right? If we look at like this section, our rise was 1. That was at my change in x, right? It was 1. And my run is 10. If I go like over there, rise is 1, run is 10. And that's how we got our 1 divided by 10, or 0.1 meters per second. And over here, my rise is 0. Well, as soon as the rise is 0, the slope is 0. So you can think of this as just a slope. And if you remember, slope we defined in Algebra 1 as m is equal to y2 minus y1, which is y final minus y initial, which is delta x in our case, over x final minus x initial, which is delta t in our case, because I know it sounds weird saying the y final minus y initial is delta x, but remember, x is on your y-axis here, and t is on your x-axis here. So if you think of it as rise over run, it should make sense. The rise is how much I change in x, and the run is how much I change in y. So you can think of this as a slope. If we look at our third time interval, down here, my initial position is 2. My final position is 0, right? Because this is the point 15, 2. So the initial position is 2. This is the point 20, 0. So the final position is 0. So if I'm looking from 15 to 20 seconds, I would have delta x is 0 meters minus 2 meters, because final minus initial. And then if you subtract that, you would get negative 2 meters, which the negative sign's representing that we're actually doing a displacement. We're doing a vector, not a scalar. The negative tells us we went backwards. And then delta t is just 15 minus, or sorry, 20 minus 15, which would be 5.0 seconds. It would be very odd if t was ever negative. And then v bar for the last section would be negative 2.0 meters over 5.0 seconds, which would be negative 0.40 meters per second. And again, we see that negative sign, which means this is a vector and it's going backwards. All right, the second graph I have, if we look at this, this is a velocity versus time graph. Velocity is on the y-axis, time is on the x-axis. We'll talk about this in the next month's lesson as well, because I'm going to talk about accelerations then, but we're not doing that now. For now, we're sticking to our same equation that v bar, our average velocity, is delta x divided by delta t. Again, that means average velocity is change in position divided by change in time. And if I look at that, it asks us, how far does the particle move during the first 4 seconds? Okay, well, I already know delta t is 4, so let's do that part. So we're doing from 0 to 4 seconds. All right, we'd have delta t is 4, obviously, seconds, 4.0. And if we look at our scale here, 0 seconds is here, 4 seconds is there. We're looking at this region here. And if I'm looking, I need to figure out, well, I know velocity this time, okay? I know, so I have to figure out, but if I look at my equation, I'm looking for position, and I have to figure out my average velocity. And average velocity, well, we said an average is just add up and divide by 2. I'm pretty sure I mentioned that anyway. Hopefully I mentioned that. Yep, right there. Add them up and divide by 2. So if I look at my final velocity is 5.0 meters per second. And my initial velocity is 0 meters per second. And I'm just going to divide that by 2. So my v bar is actually 5 divided by 2, or 2.5 meters per second. Now, I can't use this equation quite the same way that I did before, because I'm looking for a different quantity. So if I think about my equation, v bar is equal to delta x over delta t, it asks us how far does the particle move? Well, if I'm looking for how far, I'm looking for delta x. I'm looking for the change in position or the displacement. So I'm just going to go and solve this equation for delta x. So I'm going to multiply both sides by delta t to get delta x by itself. And I would have delta x equals v bar delta t. And I found both of those values on the graph already. I really should have done that before I did anything else, but that's all right. So if I think about that, v bar we said is 2.5 meters per second, and delta t is 4.0 seconds. And if we look at the units, the seconds would cancel because one's in the numerator and one's in the denominator, just like converting units. We're not converting units, we kind of are, but not really. So we end up getting just meters left over, which makes sense, or it should make sense anyway. And if you do 2.5 times 4, you would get 10 meters per second. If I really wanted to be technical, I would do 1.0 times 10 to the first, just so we knew that we have 2 significant digits. So 10 meters per second. Now, the other thing that I wanted to note there is that if we look at what quantities we're multiplying here, we're taking the velocity, the average velocity times time, times change in time. The average velocity, the velocity is your y value, and the time is your x value. And so essentially what we're doing is we're actually taking the average velocity times the time. So we're doing this height times this base, and we're finding the area of this rectangle is essentially what we're doing. Finding the area of that rectangle, if you remember from your grade school days, is the exact same thing as finding the area of this triangle. And if you think about the area of the triangle, it's half base times height. Half of 4, because the base is actually 4 long since we're going by 2's, times the height, which is 5. Half of 4 is 2 times 5 is 10, which is the same thing that we just got. So we are actually finding the area underneath that curve to find the displacement. And that is if you are given one where they don't give you nice numbers, or it's not something convenient, you can find the displacement doing that. To do that, though, I mean, in this case, we could do it geometrically, but if it wasn't such a nice straight line, we'd have to use calculus to do that. And the calculus students will probably explore problems like that when you get into integration, which will probably be second semester. But that's all right. For now, we don't need to worry about it. All right. They want us to figure out 4 to 6 seconds as well. And actually, I'm going to do it area-wise first. Okay, I'm going to try thinking of it area-wise first. If I think of this as 4 to 6 seconds just being the area underneath this line here, well, this is 2 wide by 5 tall. 2 times 5 is 10. Now let me do it equation-wise as well. If I'm going 4 to 6 seconds, well, delta t is obviously 2 again. Or not again, but 2 this time, because 6 minus 4 is 2. And v bar, well, this whole line has a y value of 5. So if the ending value is 5 and the beginning value is 5, v bar is going to be 5 the whole time. And then if I use that same equation that I solved for before, the delta x equals v bar delta t, which is not a new equation. It's just me modifying the definition of velocity, average velocity, to solve it for delta x. I would end up finding that I get 5 meters per second times 2 seconds, which is 10 meters again. And once again, the seconds would cancel, which gives us the units that we want. If somebody asks you, well, how far did you travel total from 0 to 6 seconds, you would just say, oh, well, okay, I had 10 meters per second in the first part and 10 not meters per second. I screwed up the units there. Oh, somebody could have corrected me on that in class. You can see I canceled them, but then I wrote it anyway. I apologize for that. But if I took the 10 meters from the first part and 10 meters from the second part, well, going from 0 to 6 seconds, that's 10 plus 10 or 20 meters. And I am going to stop there so this file doesn't get too